I am Prabhakar. Today we will discuss the motion of an object in a straight path when it is having constant acceleration. Let us look at this graph which is there in front of us. Velocity has been plotted against time. Velocity is varying constantly with time. Plot of v versus t, which is a straight line given by this line, it means the slope of this is constant. The velocity varies constantly with time. It means the average acceleration, which is delta v by delta t, is constant. That is, this is delta v and this is delta t, that is a constant. It is the same as in any other interval delta between these 2 points, and thus the slope is all same because it is a straight line. When we say it is a straight line graph, it has a constant slope. Now, in that case, how do we determine the acceleration? Acceleration is simply delta v by delta t. If I apply to the extreme points, that is v minus v 0 by the time interval, that is t. It means the average acceleration is the same as the instantaneous acceleration. It means a t is equal to v minus v naught. It means v at any time is velocity at 0 time plus acceleration into t. Now, this is one of the equations of motion of an object moving with constant acceleration along a line. Consider the velocity time graph for a constant acceleration case. That is, the acceleration is constant. It means the velocity varies uniformly with time given by the relationship v equals v naught, that is velocity at any time is velocity at 0 time plus the acceleration into time. The velocity varies constantly with time, that is why you said constant acceleration. Now, in this graph, in the interval 0 to t, look at this portion, the acceleration is 0 from 0 to t if you consider this as the portion where the velocity remains constant. When the velocity remains constant, that is the average velocity is the same as instantaneous velocity during the interval. Now, the area under this graph, which is given by v 0 t, is a measure of the displacement in the interval 0 to t if the object were to move with constant velocity. Now, because the velocity is changing, there is an additional area which is coming up. Now, because velocity is changing, then we need to find out the area under this. This is because the accelerated motion. Now, this area which we have got is because the object is moving with constant velocity. Now, what is the area under this graph, that is, which has the base as v 0 and this interval is t, and this vertical this thing which is the difference in velocity is v minus v 0. So, the area of this triangle is given by half into v minus v 0, that is the height of this triangle, and the base of this triangle is t. Now, this is the area corresponding to the triangle represented here in the figure. So, this is the additional displacement. Now, this additional displacement has come about because there is an acceleration. So, the area here is half into v minus v 0 into t. Now, the total area under the curve between 0 to t under v t curve, under velocity time curve, is v 0 t plus half into v minus v 0 t. Now, this is the displacement that the object has undergone in the time interval 0 to t. The total displacement is because of the constant velocity motion, considering that it is a constant velocity motion, plus the contribution because of the accelerated motion. v 0 t is the contribution from the constant velocity motion. This is the additional part that is contributed by the accelerated motion. if you find this area which gives you the total displacement, because when the velocity is changing, the total displacement under the velocity time graph is v 0 t plus half v t minus half v 0 t. Now, if you know the relationship in terms of, if you want to remove this v, because which is a velocity at time t, then we use the first equation which we have already derived, where the velocity varies with time, but constantly. It means acceleration remaining constant. We can substitute v 0 t plus half. For v, we will write it as v 0 plus a t into t minus half v 0 t, which when simplified becomes v 0 t plus half v 0 t plus half a t square minus half v 0 t. So, this half v 0 t and this half v 0 t cancels, and we get v 0 t plus half a t squared. What is this? This is the area under the velocity time graph, which represents the displacement, or which gives you x minus x 0, where x is the displacement at time t, x 0 is the initial displacement. Now, this x minus x 0, which is the displacement, if I use the symbol s, x minus x 0 is the change in position coordinate. If s is the displacement, s is equal to v 0 t plus half a t squared. In other words, x minus x 0 equal to v 0 t plus half a t squared, or the position at any time t is the initial position plus the change in position because of constant velocity, considering that the object is moving with constant velocity with the initial velocity, plus the contribution because of the accelerated motion, which is a t squared. So, the position coordinate x is initial position plus the change in position because of the velocity being considered constant, and the additional factor is because of the change in velocity, which is if the velocity change is constant, and we write it as half a t squared. So, this is the relationship between position coordinate of at any time t with the initial position coordinate and the initial velocity and the acceleration, which is assumed to be constant and the time. Now, this is one of the equations of constant acceleration motion. The equation in the box is one of the equations of motion for constant acceleration case. The other equation is about the velocity relationship. Velocity at time t is velocity at time 0 plus a constant acceleration a times t. This gives you the velocity at any time t. This is also one of the equations of motion, which relates how the velocity changes with time constantly. If the acceleration is 0, then the final velocity would be the same as the initial velocity, or the v will not change. But here, if there is an acceleration, then we have velocity at any time t, initial velocity plus acceleration. This is one of the equations. Now, how velocity changes with time. The equation x is equal to x naught plus v 0 t plus half a t squared is how position coordinate changes with time in one dimensional motion, where the initial position is x 0, the initial velocity is v 0, and a, which is a constant of motion. This relationship can be considered the second relationship. The second relationship is about position and time and acceleration. The first relationship is about velocities and time and acceleration. Now, in these two equations of motions, we have time as a variable. Now, if you want to relate these two, removing time as a factor, then how is x, x naught, v 0 and a related? if you remove t by eliminating t in these two equations, we get the relationship x minus x naught, that is for substituting for a, then you have x minus x naught equal to v 0 into, for time I am substituting in that equation, v minus v 0 by a, that is substituting equation 1 into for a, then you have plus half a, for time squared I have to substitute v minus v 0 by a whole squared. So, x minus x naught equal to v 0 into v minus v 0 by a plus half a squared in the denominator becomes a in the denominator, and you have v minus v 0 whole squared. This can be simplified further, and you have the result x minus x naught, you have a here, multiply a 2a on the left hand side, you have 2a into x minus x 0 as v 0 v minus v 0 squared plus v minus v 0 squared becomes v squared minus 2 v 0 plus v 0 squared. Now, the equation 1 which is indicated in the box relates velocity at any time with the velocity, initial velocity plus the acceleration. The second equation which is written in the box relates position coordinates and time and acceleration. If we want to eliminate t between these equations, then we have x minus x naught is equal to v 0 minus v naught by a, because I have put for t I have substituted v minus v 0 by a. Similarly, I have plus half a t squared, I have written it as v minus v 0 by a whole squared. Now, when simplifying this, we have x minus x naught on the left hand side equal to v 0 into v minus v 0 by a plus half a half into v minus v naught whole squared, and in the denominator we have a. Multiplying this equation by 2a all through, I get on the left hand side 2a into x minus x naught is 2 times v 0 minus v 20 v 0 v minus 2 v squared plus v squared minus 2 v v naught plus v 0 squared. It means 2 a x minus x naught equal to v squared minus v 0 squared, or v squared is equal to v naught squared plus 2 times acceleration into change in position coordinate x minus x naught. This result relates how the velocity at the position coordinate x can be determined if you know the initial velocity and the acceleration and the initial position coordinate. So, the equation v squared is equal to v naught squared plus 2a into x minus x naught. Now, x minus x naught measures the displacement, the change in the position coordinate, and v and v 0 are the changes that have occurred in terms of velocity at the position x, v 0 corresponding to the velocity at position x 0, and a is the constant acceleration. This is the equation that we have obtained from the kinematics of relationship involving displacement and time and velocity and time, and this is can be considered as a third relationship, but we obtained this third relationship from the two basic equations, namely velocity is v 0 plus a t, how velocity changes with time given constant acceleration, and how x minus x naught is v 0 t plus half a t squared, or we wrote it as x is equal to x naught plus v 0 t plus half a t squared. I am marking it again. V equals v naught plus a t is a relationship that gives how the velocity changes with time for constant acceleration case. This relationship x is equal to x naught plus v 0 t plus half a t squared gives how the position coordinate changes with acceleration and time given the initial velocity and the initial force. Now, these are the relationships for involving various variables like velocity, acceleration, time and change in position coordinate. Now, the velocity variation with time is v is equal to v 0 plus a t, which one of the equations of kinematics of constant acceleration case. The other one which is relates change in position coordinate x minus x 0 is v 0 t plus half a t squared. This equation sometimes is also written, equation number 2 is also written as s, that is x minus x naught is change in position coordinate, where we have represented this as s the displacement, s is v 0 t plus half a t squared. Now, instead of change in position coordinate, if they give the change in position coordinate directly and say this is the displacement. Now, the second equation, which is x minus x naught is equal to v 0 t plus half a t squared. In many times this is also referred to as s, this is x minus x naught, which is the change in position coordinate, is represented by symbol s, where s denotes the displacement of the object, that is changing position coordinate is called the displacement, and that is s is equal to v 0 t plus half a t squared, which is the second equation. Both these equations 1 and 2 involve time. The third equation which we obtained is the combination of the equations number 1 and 2, sometimes written as v squared is equal to v naught squared plus 2 a into x minus x naught. Again this equation, even the modified form where x minus x naught is represented as s, becomes v squared is equal to v naught squared plus 2 times a into displacement, where s refers to x minus x naught, which is the displacement. The kinematical equations for constant accelerations are v equals v naught plus a t, s is equal to v naught t plus half a t squared, and v squared is equal to v naught squared plus 2 a s. We will see the applications of these equations of motions of one dimension in the next class.